erratic motion is defined as position, velocity, acceleration cannot be described by a single continuous mathematical function along the entire path. Right? When you first hear the term erratic motion, you might think that it is something that has to be really jerky or really erratic all over the place. What about when you drive your car? Maybe it's like that. Maybe you're a crazy driver. But maybe you're not. Maybe you're a very safe driver. Maybe you're a grandma driver, you know? And if you are, it's still erratic motion. Could you write a single mathematical equation that accounted for all of the different things you do when you drive your car? No. You could write multiple mathematical equations, but as you let off the gas, you know, and you slow down, that's one acceleration. You hit the gas again, that's another one. Things are changing. That's erratic motion. Okay? So erratic motion is just we don't have that one constant acceleration, or we don't even have a non-constant acceleration that stays. We have a changing acceleration that can't be described by a single mathematical function. And so you guys brought up, at the very first day, I was asking what you remember about statics. And I think, what was it? Shear and bending moment diagram graphs came up. And I said, we're not doing that. Did anybody have a sigh of relief? Okay, well, this is going to crush that. I apologize. Although we're not doing that, we're doing something very, very, very similar. And we're doing erratic motion graphs. With erratic motion graphs, we have a relationship. It is not an integral relationship like what we used in shear and bending moment diagrams. It's a derivative relationship. It's the opposite. Okay? What's our relationship? It's right there. Our first kinematic equation, velocity is equal to the derivative of position. So if we have a graph of position, we look up here, this is our position versus time, or our ST graph, position versus time. If we have a position versus time graph, at any given point, the derivative is equal to the slope. So that's telling us that the velocity, the value of velocity, so whatever the velocity is at any given time is going to be equal to the slope of position. So at any given time, we can figure out that slope, and then we can plot it. Right here, we'd say, well, the slope is this value. And it's a little bit less, and now it's negative, and that is our velocity graph. Make sense? From our position graph, we can get our velocity graph with doing nothing else but taking the derivative. Okay, as you would expect, we continue that relationship to velocity, or to acceleration. We have the exact same relationship that the value of acceleration is going to be equal to the slope of velocity. So if we have a velocity, a VT graph of velocity versus time, we can make our acceleration versus time just by taking the slope at any given point, plotting that as the value, and then connecting the dots. We got ourselves an acceleration graph. From VT, finding the VT from the AT is just going backwards. This would be the same relationship as our shear and bending moment. How do we know? Well, we start with this equation, and then we say, I'm going to say ADT equals dV, and I'm going to integrate both sides. This is going to go from V naught to V, and this is going to go from 0 to T. We'd end up with V minus V naught is equal to the integral A dt. Or we could also write the change in velocity, which is V minus V naught, is going to be equal to the integral of A dt. Writing that in words, this is change in velocity is going to be equal to, what is this graphically? What's an integral graphically? Very good, the area under the curve. Change in velocity is equal to the area under the acceleration curve. Of course, we can do the same thing for our velocity. Okay, they kind of give a pictorial demonstration here on the slide as well. You would, when you're going backwards, just like when you do integration, you use the plus c, right? We need to know something else. We can't directly find the velocity from the acceleration unless we know initial velocity. So we'd first have to find initial velocity from some other means. Then we would measure how much area is under the curve. We'd go up that far for that given t, and then we just kind of keep going. And we can construct our graph. Okay? We can do the same exact thing for position using our initial v equals ds dt. V dt equals ds, integrate. We end up with s minus s naught is equal to the integral of v dt. Or change in position is equal to the integral of v dt. Change in position is also called what? Change in position is displacement. Displacement. Change in position, or displacement, is equal to area under VT graph. Any questions about those relationships? All right, I have a couple example problems. Let's see which one we want to do. I think I will do a simple example for you, and then we'll do a less simple one together. Yeah. Because we're kind of in a hurry now. Not a hurry, but there's one thing I want to get to by the end of the day. So, the sports car travels along a straight road such that its position is described by the graph. Constructs the VT and AT graphs for the time 0 to 10 seconds. Notice that for here we do have to break it up. In the last problem I said you don't have to break it up. Here we do. We have to break it up from 0 to 5 seconds and from 5 to 10 seconds because that's when the equation changes. So we'd start off with our givens. We are given nothing else but the ST graph. We want to find the VT and the AT. What's the relationship that we're going to use? Are we using a derivative or an integral relationship? No, we can't use derivative, unfortunately. Oh, to go from S to V. Yeah, you're right. Sorry. We are using derivative. We're using the easy one, right? We're using the derivative relationship because velocity, which we want to find next, is equal to ds dt. And acceleration is equal to dv dt. Derivative relationship. So how I like to do these is just break them up into the different categories. We'll say 4. 0 is less than or equal to t, which is less than or equal to 5. Our equation is s equals 3t squared. Velocity is 6t. Okay? 4. 5 is less than or equal to t, which is less than or equal to 10. We have s equals 30t minus 75. And position is therefore, velocity is equal to what? 30. do that part. We're going to do our VT graph now. Okay, when you're doing graphs, it's very important that you don't try to make a scale on the graph and then draw a graph and make whoever's reading your work try to figure out where that falls on the scale. Okay? That's not the way that you graph. When you graph, you're trying to display information. Yes, it's kind of fun to make a pretty graph where somebody has to guess, but it's much more important to show that you know the numbers, exactly what the numbers are, whenever it crosses the x-axis, whenever there's an inflection point or a change. So what I like to do is just mark off this 5 and the 10, because we know those are important points. From 0 to 5, we know that v is going to be equal to 6t, so I can plug 5 in for t to see where it would be at. And it would be at 30. So I'm going to put this and mark this right at 30. I know it's a straight line because it's a linear equation. So there we go. V equals 6t. Oh, I had the wrong. This is meters per second. Okay, from there, v equals 30. We have a straight line. Any questions about that? Okay, continued acceleration. Acceleration's even easier for this one. 4, 0 to 5, acceleration is equal to 6. From 5 to 10, acceleration is equal to 0. There we go. We just constructed a VT and an AT plot from an ST plot. However, I got to complicate things, right? That was probably a pretty simple relationship that we just looked at. But there's another kinematic equation. The third kinematic equation is the one where t is left out. And this one is where a monkey wrench is kind of thrown in. Our equation is the integral is v dv equals ads. V dv equals ads, and we want to know how to relate those graphs. So we're just going to integrate both sides. When we integrate both sides, we're going to go from initial velocity to v, and we're going to go from initial position to s. We end up with 1/2 v squared minus v naught squared is equal to the integral s naught to s a ds. Notice that I can't take a out because we want this to go for everything, not just constant acceleration. Okay, then we can solve for v by multiplying both sides by 2. V squared minus v naught squared. And then I got to put the v naught squared on the other side. And if I wanted to, I could take the square root of everything to get my actual v. Okay, so now how would we make a graph? Well, it turns out the only difference is you have to do a little algebra. Okay? We'd start out with our v naught, and then when we want to find our v1, we would find the area under the AS curve. The area under the AS curve is just the integral ADS. You find the area under the AS curve, that's only this part. This is area under curve. So you'd calculate the area under the curve, plug it into this equation, and you have to do a couple more steps before you get your actual velocity. Unfortunately, that makes it a little bit more difficult to recognize common relationships, like the fact that the polynomial order goes up when you take the integral and goes down when you take the derivative. If you have a linear velocity, you expect to have a constant acceleration, and so forth. Those relationships don't hold up when you're doing an AS and a VS graph. Okay? That's very important to remember because I see that mistake a lot. So the AS and the VS graph don't have those same relationships. You have an equation. You use the equation just like you do in other math. Going the other direction, from AS to VS, we do something very similar. We're just going to divide both sides by ds. And we end up with acceleration is equal to v dv ds. Well, what's that telling us in words? It's telling us acceleration is equal to, what's v? Come on, that's an easy question. What's v? It's not position, it's not acceleration, it's velocity, okay? It's going to be equal to velocity. What's dv ds? Very good. The derivative velocity with respect to position. How would you see that on the VS curve? If I have a VS plot over here, it'd be the slope. Very good. dv ds multiplied by the slope of VS. So if you have a VS curve and you want an AS curve, all you have to do is go to this curve over here and say, well, the value of velocity is whatever this value is, and the slope is whatever that is, multiply them together. Multiply the value times the slope, you get acceleration. That make sense? Here we go. The VS graph for a go-kart traveling on a straight road is shown. Determine the acceleration of the go-kart at s equals 50 and s equals 150 meters. Draw the AS graph. I'd like you to do this in your groups. Working with someone, you're going to need someone to talk to, so if you've been working by yourself, find somebody to ask questions to. This is actually a pretty quick one to answer, but it is a little confusing. So see if you can figure this out. I'll write the givens and finds, then I'll come around and answer questions. So this is actually a very simple problem to solve. I bring it up here because it's not really that intuitive, right? You want to look at a velocity equation graph, and you want to use the slope of that velocity graph as your acceleration. And that works great if it's a velocity versus time graph. And this is not. This is a velocity versus position graph. They do not have the same relationship. The relationship they have is dictated by this equation. And we can just divide by ds to solve that equation and say acceleration is equal to v dv ds. Thanks. There we go. Acceleration is equal to v dv ds. We just have to know what that means. V is just velocity, or the value at where we're asked for. At 50, since this is a linear function, the value's got to be 4. dv ds is the slope. What's the slope? Rise over run. Rise over run would be 8 over 100, which would be equal to 0.08. So we end up with acceleration equals 4 meters per second times 0.08, which equals 0.32 meters per second squared. Questions about that? Okay. We do the same thing for the next point, which is right here at 150. Value for v is the same. The slope is the same. It's just negative. And we end up with 4 times negative 0.08, which is negative 0.32 meters per second squared. Okay, so just keep in mind that the relationship is not exactly the same as with AT and VS.